Good morning, everyone. I thought we could go over the first integration by parts homework together. Let's start with problem number 1. This is problems 1 through 14 on this page. Integral of x sine x dx. And so we're going to make our little box. Remember, I have to put an antiderivative here and something I want to do the antiderivative of here and something I want to do the derivative of here. Well, I'd much prefer to do the derivative of x and put sine x dx here. So the derivative of x is going to be 1, and the antiderivative of sine x is negative cosine x. Remember, our recipe is this times this, so negative x cosine x minus the integral of this times this, negative cosine x dx. So I'm going to pull that negative out. And then I'm going to integrate cosine. So I'll have negative x cosine x plus sine x, and don't forget the plus c. There's number 1. 2. Integral of x e to the x dx. Okay, so for this one, I'm thinking about my box. And again, choice between taking the derivative of this and taking the derivative of this. I could certainly take the derivative of this, but if I do the antiderivative here, this will just get higher and higher in power, and I'd like this to go away. So I'm going to take the derivative of x and put e to the x dx down here. Derivative of x is 1 dx. Antiderivative of e to the x is e to the x. Following our recipe for by parts, this times this, x e to the x minus the integral of e to the x dx, because we're doing this times this. Okay, so that's x e to the x minus e to the x plus c as our antiderivative. All right, how about number 3? 3 says the integral 3t e to the 2t dt. So 3t, 3 dt, e to the 2t dt. Now, what's the antiderivative of this? It's not e to the 2t, because if I think about taking the derivative of e to the 2t, I'd have e to the 2t times 2. And there's no times 2 here. There must be something present on the original antiderivative that gets rid of this 2 that should show up. So I have e to the 2t over 2. Let's try that. Y equals e to the 2t over 2, or 1/2 e to the 2t. Now, if I take the derivative of that, I still have 1/2 e to the 2t, but when I use chain rule and take the derivative of the inside function, I'm going to have a times 2. That times 2 and that 1/2 will cancel out. So please note, every time I go backwards with this one, I have to have another divide by 2. That'll become important in a moment. So 3t times e to the 2t over 2 minus the integral of 3 times e to the 2t over 2 dt. So here, I kind of want to tidy things up and turn that into 3/2 t e to the 2t. And here I've got another 3/2 that I can pull out as a constant, e to the 2t dt. And what did we say the antiderivative of e to the 2t was? It's e to the 2t over 2 times the negative 3/2 that's already out there. Don't forget 3/2 t e to the 2t and the plus c. So our final answer is 3/2 t e to the 2t minus 3/4 e to the 2t plus c. Number 4. 4 says the integral of 2t cosine 3t dt. Well, I'm putting 2t here. This is 2 dt. This is cosine 3t. But the derivative isn't sine 3t, right? Because if I took the derivative of this, I would have cosine 3t, but chain rule says I would have a times 3. There's no times 3 here, so there must be something over here in this original antiderivative that gets rid of that. You know, if you're not comfortable thinking backwards this way, you can always just do the u sub, cosine 3t dt, where u is 3t and du is 3 dt. Du over 3 equals dt. And so we're looking at cosine u times du over 3. We can pull that 1/3 out in front. And so now we're just integrating cosine. We've got 1/3 sine u. So notice that 1/3 is coming out because of the derivative of the inside function, the derivative of our u. Okay, so using by parts formula, 2t times sine 3t over 3 minus the integral of 2 times sine 3t over 3 dt. Well, I'm going to tidy things up again. I'm going to have 2/3 t sine 3t minus 2/3 integral sine of 3t dt. So now I have to do the antiderivative of this. Again, I can do it as a u substitution, or I can say, well, I know the antiderivative of sine is negative cosine, but I also need to undo that times 3. So I'm going to have that negative 2/3 and negative cosine 3t, but over 3. So I'm going back again. I need another 3. And here, 2/3 t sine 3t. So negative times negative is positive, and 3 times 3 is 9. So I would end up with 2/3 t sine 3t plus 2/9 cosine 3t plus c. And there's number 4. Let's take a look at 5. 5 I'd like to do two ways. Integral of x squared cosine x dx. So the first is with our box method with x squared 2x dx, cosine x dx, and sine x. So then I'd get x squared sine x minus the integral 2x sine x dx. Okay, so now to integrate here, I'm going to have to use the box again. Don't suddenly put the trig function up here. You'll simply undo what you just did and get back to where you started. Instead, if you put a polynomial function here, continue putting a polynomial function here. 2 dx sine x dx negative cosine x. Watch your SIGNs here. Look, we've got this minus here, we've got this minus here, and then when I do the integral here, there's going to be another minus. So we've got the original x squared sine x, then we have our minus, then we have this times this, 2x negative cosine x minus the integral of 2 times negative cosine x dx. I think these brackets are really important. They help me remember that I need to distribute this negative not just to here, but also over to here. But this goes with this too. Oh, so many negatives. So we get x squared sine x minus a minus is plus 2x cosine x, and then we've got minus a minus is minus 2 times the integral of cosine x dx. That's a pretty easy one for us to do. So we've got x squared sine x plus 2x cosine x minus 2 sine x plus c. You know, it's a pain in the butt to do by parts twice or even 3 times. But some clever boffins have come up with tabular integration, where we choose one function to take derivatives of, and the other function to take antiderivatives of. So here my derivatives will be 2x, 2, and 0. Here my derivatives are going to be, my antiderivatives are going to be sine x, negative cosine x, negative sine x. We're not connecting across, we're connecting on the diagonal. And just like magical cofactor fabric from matrices, you need to put in a little thing here, a little deus ex machina, to make it all work. We multiply by a positive, we multiply by a negative, we multiply by a positive. This accounts for every time we're going backwards, we have this minus in front of the integral. So alternating the signs, every time we go back one, look, that minus and minus has now become a plus. Okay, so what would our answer be? Well, this one times this one, x squared sine x. This one times this one, that's positive times positive, 2x cosine x. And then this one times this one, negative 2 sine x. Grant, don't forget the plus c. Okay, and I think most people would say, wow, that's a lot faster. Why would I ever do the other method? I will show you some problems in this video, perhaps, but definitely in the next video, where we're going to be doing by parts, and this wouldn't help us at all. So, number 5, x squared sine x plus 2x cosine x minus 2 sine x plus c, whether I do by parts twice or if I use tabular. I'll do by parts twice once more, but then I'm going to be using tabular whenever I can. Let's take a look at number 6. So 6 says the integral of x squared e to the minus x dx. Okay, so by parts twice, x squared, 2x dx, e to the minus x dx, e to the minus x. Wait a minute. If I take the derivative of this, shouldn't there be a negative here? So when I go backwards, there must be something there. You can do this as a u sub, where u equals negative x if you want to. So we end up then with this times this, or negative x squared e to the minus x, minus the integral of 2x times negative e to the minus x dx. That's going to be negative x squared e to the minus x. Negative times negative is plus. I'm going to pull out that constant 2, x e to the minus x dx. And now I'm ready to do my second by parts. X e to the minus x dx. The derivative of this will be 1. The antiderivative of this will be negative e to the negative x. So then we've got this times this behind that 2. Negative x squared e to the negative x plus 2 times negative x e to the negative x minus the integral negative e to the negative x dx. Oh, look at all those signs. So, and don't forget to distribute this too. Negative x squared e to the negative x minus 2x e to the negative x. Negative times positive will be plus 2 e to the negative x dx. So then my antiderivative ends up being negative x squared e to the negative x minus 2x e to the negative x minus 2 e to the negative x, right? Because I have to pull this negative out for the antiderivative, so that negative times that positive made that. And don't forget the plus c. Okay, so if I'm doing this problem with tabular, I'm thinking about x squared, 2x, 2, and 0. I'm thinking of e to the negative x, and then I go backwards, and I have negative e to the negative x. And I multiply that negative that came out the first time times the negative that's going to come out the second time, and now I'm back to positive e to the negative x. And then, again, another negative comes out, and I get negative e to the negative x. Remember, we don't multiply across, but we multiply on the diagonals here. And we don't bother with this one because 0 times this one, nothing would happen. Plus, minus, plus. Okay, so I have this times this, which is negative x squared e to the negative x. I have negative times this, or negative 2x e to the minus x. And then finally this times this, which is negative 2 e to the negative x plus c. That really does equal that. So I like tabular. Tabular, 6. It'll be big one day. 7 with tabular. 3x squared e to the 2x. 6x, 6, 0. Be careful here with that 2. Every time you go backwards, you have to divide by another 2. So the first time, it's going to be e to the 2x over 2. And then it's going to be e to the 2x over 4. And then it's going to be e to the 2x over 8. So on the diagonal, we get these values. And we'll say 3x squared e to the 2x over 2. Oh, I forgot my signs. Minus 6/4 x e to the 2x plus 6/8 e to the 2x plus c. Me, I'm going to tidy this up. E to the 2x minus 3/2 x e to the 2x plus 3/4 e to the 2x plus c. All right, 8. 8 says the integral of x squared cosine x over 2 dx. Well, I've got x squared, I've got 2x, I've got 2, I've got 0. This is cosine x over 2. What's its antiderivative? Well, let's think about that. Cosine x over 2 dx. Let's say u equals x over 2. du is 1/2 dx. Well, I don't have a 1/2 to go with the dx, so I'm going to multiply both sides by 2. 2 du equals dx. So it's the integral of 2 cosine u du. Notice there's this 2 that's coming every time I take an antiderivative. So this will be 2 sine x over 2. This will be negative 2, another 2 comes out, 4 cosine x over 2. And then we'll have positive 8 sine x over 2. On the diagonal, don't forget plus, minus, plus. And so we end up with 2x squared sine x over 2. Minus a minus is plus 8x cosine x over 2. And then we've got a positive 2 times 8 for 16 sine x over 2. Don't forget the plus c. And there's problem number 8. We're a little more than halfway done with this assignment. 9. Integral of y ln y dy. So, you may be thinking that tabular is all that, and then you come to a problem like this. And you say, okay, I'm going to put y here, and 1, and 0. But over here, you've got ln of y. What's the antiderivative of ln? No, it isn't. Look, I didn't even have to wait for you, because I knew that you weren't going to come up with the antiderivative. I know the derivative of this. This has to go over here. Oh, I don't want to do this. Instead, I'm going back to this method. But instead of putting the y here, I'm putting the y here. And the ln here, because I know how to take the derivative of ln. That has to go here. So the derivative of ln of y is 1 over y dy. The antiderivative of y is y squared over 2. Yes, that did get bigger, but don't worry, it'll all work out. So this times this, y squared over 2 ln of y minus the integral y squared over 2 times 1 over y dy. Well, here I'm going to simplify, and I'm going to pull the constant out. So I have y squared over 2 ln of y minus 1/2 integral y dy. That's going to give me y squared over 2 ln of y minus 1/2 y squared over 2 c. And so I'll probably write this as y squared over 2 ln of y minus y squared over 4 plus c. That would be my answer to number 9. And I didn't use tabular. 10. When I look at 10, I think, oh, that's tabular, right? Yeah, no. That ln over there, that says it's not tabular. dt. Okay, so by parts, t squared? No, ln of t. 1 over t dt. Here's where the t squared goes. The antiderivative of t squared is t to the third over 3. So I multiply these together. I get t to the third over 3 ln of t minus the integral t to the third over 3 times 1 over t dt. These can cancel. I'm going to pull the 3 out. So I have t to the third over 3 ln of t minus 1/3 integral t squared dt. So that's going to be t to the third over 3 ln of t minus 1/3 times t to the third over 3 plus c. And I will tell you this out because I'm my mother's son. ln of t minus t to the third over 9 plus c. As far as tidying it up goes, I've never seen one of these problems on free response. This is a multiple choice problem, which means that's what you're going to see as the choice. You're not going to see this. So I don't care if you simplify, but you need to be able to find the simplified problem or simplified solution. Okay, 11. Now we're going to tie this back together with what we were doing at the beginning of the chapter where we were solving differential equations. Number 11 says you've got this differential equation dy dx equals x plus 2 sine x, where y of 0 equals 2. All right, so we know we're supposed to do separation of variables. X plus 2 sine x dx. And then we're supposed to integrate. And so the antiderivative of 1 dy is y. And over here, oh, I've got a function and someone else's derivative. That means it's a by parts problem. So I put x plus 2 here, and 1 dx is the derivative. I put sine x dx here, and the antiderivative is negative cosine x. So the integral will be this times this, x plus 2 negative cosine x, minus the integral negative cosine x dx. Minus a minus is plus, and so I get x plus 2 minus cosine x plus the integral of cosine x dx. Well, we know the antiderivative of cosine is sine, so we've got negative x plus 2 cosine x plus sine x plus c. But wait, they've given me an initial condition. They say y equals 2 when x equals 0. Well, we know the sine of 0 is 0. Cosine of 0 is 1. 1 times 2 is 2 times a negative. I have a minus 2 there, equals 2. So c equals 4. Remember, they want to see you using that initial condition, or you're going to lose at least 1 point, if not 2. Sometimes where the reader is told to stop reading if they don't see the initial condition being used. Okay, so finally we get y equals negative x plus 2 cosine x plus sine x and plus c, or plus 4. Here's my answer to number 11. 12 says dy dx equals 2x e to the minus x, and y, y of 0 equals 3. Okay, we'll do separation of variables. We'll integrate both sides. I'll say, aha, you're by parts, because I see a function and someone else's derivative. So 2x is the function, the derivative would be 2 dx. Here's the derivative of someone else's function, e to the minus x dx. Its antiderivative, remember that minus, is minus e to the minus x. So my integral will be y equals negative 2x e to the minus x minus the integral of 2 times negative e to the minus x dx. Well, again, watch out for those negative signs. Y equals negative 2x e to the minus x plus 2 times the integral of e to the minus x dx. All I need to do is go backwards with this, not forgetting that negative that's going to come out, and I'll be ready to use my initial condition. Remember, that negative came out. Negative times that positive gave me that negative. So now I know that 3 equals negative 2 times 0 e to the minus 0 minus 2 e to the minus 0 plus c. So that's 3 equals 0 minus 2 plus c, or c equals 5. Not quite done yet, not until we plug that c value back in. 2x e to the minus x minus 2 e to the minus x plus 5. Only 2 problems left. Let's take a look at 13. 13 says dy dx equals x secant squared x, where u of 0 equals 1. Oh, and that's not a dy, that's a du. Okay, so I see a function and someone else's derivative. X1 dx secant squared x dx tan x. So this times this. Oh, I guess I need to do separation of variables. Du equals x secant squared x dx, and then we integrate, and then we do this step. So u equals x tan x minus the integral tan x dx. And we remember how to integrate tan x. That's a u sub problem. U equals x tan x minus the integral sine x over cosine x dx. Where are u? I've got u in this problem already, so I'm going to use a w. W equals cosine x. dw equals negative sine x dx. So negative dw equals sine x dx. So all of this can be replaced with negative dw. And this is replaced with u. So then I've got x tan x minus the integral 1 over u times negative dw, 1 over w times negative dw. So negative times negative is going to give me positive. U will equal x tan x plus ln of w plus c. Remember, w was cosine of x. So u equals x tan x plus ln of cosine x plus c. And now I'm ready to use the initial condition. 1 equals 0 tan 0 plus ln cosine 0 plus c. So 1 equals 0. Cosine of 0 is 1. Ln of 1 is 0. So c equals 1. So u equals x tan x plus ln cosine x plus 1. All right, we're ready for the last problem. At last, problem number 14. dz dx equals x to the third ln x, where z of 1 equals 5. Okay, so, separation of variables, x to the third ln of x dx, integrate, and then by parts. So I'm putting ln of x up here and x to the third dx down here. I know how to take the derivative of ln of x. That derivative is 1 over x dx. The antiderivative here is x to the fourth over 4. So z will be x to the fourth over 4 ln of x minus the integral x to the fourth over 4 times 1 over x dx. I'm going to pull out the 1/4 and tidy these up. And so I'm going to have z equals x to the fourth over 4 ln of x minus 1/4 integral x to the third dx. That will give me x to the fourth over 4 ln of x minus 1/4 times x to the fourth over 4 plus c. So z equals x to the fourth over 4 ln of x minus 1/16, or x to the fourth over 16 plus c. And now I'm ready to use my initial condition, z equals 5 when x equals 1. Well, ln of 1 is 0, so I get 5 and 1/16, or 81/16 for c, which means my antiderivative would be z equals x to the fourth over 4 ln of x minus x to the 4th over 16 plus 81 over 16 plus c. Well, there was number 14. I hope that helps. And let's move on to the next video where we go through all kinds of interesting integrating by parts problems. See you there.